Okay, good morning, everyone. Welcome back to class. It's the 7th of November here, and we're working through chapter 5. So let's see. So today and Tuesday we'll finish up chapter 5, and then hopefully we'll have a nice long review there that next Thursday. And then the following week here, exam 4 will open. So that'll just cover chapter 5. Okay, so that will be our fourth and final midterm, and then we'll have a couple of weeks after that, and then finals. So, do you guys have any questions you want to go over? Anything you'd like to ask me before we get started? Anything from the homework? Or shall we just get going here? So in chapter 5, there's kind of two big ideas. The first idea is we go over experimental design, and we talk about relationships between categorical variables. And the other major thing in this chapter is the data structure, where we're looking at two categorical variables. Okay, so it turns out that it really does help to have some probability theory here in this chapter. So, so we're taking a slight break from stats and talking about probability theory. Okay, so so what do you need to know from probability theory? Well, it's mostly these rules here. So we need to know the addition rule. That's for when we're looking at an or compound event. Okay, so the general addition rule helps us to take apart that event and calculate its probability, right? So the other major rule is the multiplication rule. Okay, and the more general form of it is here. This is for the case where we have dependent events. Okay, so we have the addition rule, the multiplication rule. Then we also have conditional probability, and you can see that is part of this formula for the general multiplication rule there. So that's where we have something conditioned on something else. Then we have the complement rule, and then today, or maybe on Tuesday, we'll talk about the expected value. That's the last part we need. Okay, so that's about all we need for probability. And so we're pretty much right there in the addition rule. Okay, so that's where we were at last time. So we were using this contingency table here to help us practice with probability rules. Okay, so good. So that's where we're at, and we'll just pick up here. Okay, can you explain the shortcut for the complement rule again? The shortcut, I'm not sure. Well, the complement is basically, I think what you're talking about, Julia, is this last problem here where we have the addition rule. And so I showed you how to use the formula here, but the faster way is to simply count the number of people in the set, right? So so the formulas are great. We need them to be able to develop probability theory and to really understand what we're doing. But when it comes to calculating probability, sometimes it's faster to simply count. So does that answer your question? Okay, good. All right. So you guys, you're welcome. So you guys try a couple of these, okay? And this section we really kind of, it's sort of packed. It's almost kind of overflowing with problems. So we're not going to do all of these problems, but we'll do a few of them, enough to practice these various rules. So this first exercise is helping us to think about probability as a long run proportion. So if you have an event and you can get a sample that will tell you how many times that event happens, then you can use a sample proportion, right? And so that's what we have here. We have 400 students randomly selected, and 287 of them were taking a math class. So we should be able to use that data set, that it's a sample, to help us figure out the probability that a randomly selected student here at the college is taking a math class. Okay, so that's what I want you to do there. And then in the second problem, we're back to cards again. And so we've drawn out the whole sample space. This is what, one of these things has to happen when you draw a card from a fair deck of cards. Okay, so if you're assuming there's no joker cards in there. So I want you to practice with a couple of these probabilities. Find the probability of getting a face card. Find the probability of heart or spade. Okay, and you can use the formulas or you can count. It just kind of depends on how you like to do those. Okay, so I'll let you try these. Well, yeah, I'll just go quiet for a second and let you guys work on some of these. And as soon as you get that first one, just put it over in the chat. The probability that a randomly selected student is taking a math class. 400 is a pretty large number, right? So if you have a data set with 400 people, the law of large numbers will kick in there. So it really should be a simple proportion there. Good. Thank you, guys. That's exactly right. Perfect. Yeah. So there were 400, right? So the process is we talk to a student and see if they're taking a math class, right? And then so if we do that 400 times and 287 say yes, I'm taking a math class, then that's 0.7175. And so that if it's a well designed sample, then that really should reflect the probability of selecting just a random student and getting somebody who's in a math class. Okay, so it's pretty likely, right? A lot of our students are taking math classes here. Then let's switch over to this deck of cards. Okay, so maybe I'll get us started here. What's the probability of pulling out a face card? So the face cards are these cards over here. Okay, and so the probability of a face card, we can just count, right? So 1, 2, 3 times 4, so there's 12 out of 52, which is 3 out of 13, which is about a 23% chance. So pretty easy there, right? So I'll go quiet for about 3 minutes and let you guys work on as many of these as you can. So I'll just be quiet until about 11:42. Okay, so probability of heart or spade. Let's see here. Good. Okay, so heart or spade. Okay, so since it's an or, we know that that's going to be the addition rule. So if you want, you could just count. So that's not hard, right? So how many hearts do we have? Well, we have 12 hearts plus 12 spades, and that's I'm sorry, 13, right? We have 13 hearts, we have 13 spades, so that's 26 over 52, which is a half. And sometimes that happens with these. You get to the answer and then you realize, oh yeah, it's a half because that's 2 out of the 4 suits, right? So pretty straightforward there. And then, yeah, so Laura, the other way is to use the formula, which is to say that, well, that's going to be probability of hearts plus probability of spades. And then, so no worries. And then, so for the hearts, that's 13 over 52, and then for the spades, that's 13 over 52, which gives us the same thing, right? So it's a half, right? Okay, so a 2 or a 3. Good, yeah, that's correct, Armand. So if we go probability of 2 or 3, that's going to be probability of 2 plus probability of 3. Okay, so there are 4 2s, right? So if we look here, all of the cards in this column here are 2s. All of the cards in this column are 3s, right? So we have 4 out of 52 2s, and then we have 4 out of 52 3s. So that's 8 over 52, which is 0.1538. Okay. So it gets a little bit more complicated here when we're talking about ace or a heart. And the reason why is because there's an overlap here. Okay, and this is definitely where I would recommend counting rather than using a formula. I think it's just a little bit more likely that you'll get kind of caught up in the formula and you can make a mistake. So if we were to just count, what I would do is I would circle all of the cards that are aces or hearts. Okay, so what cards would that be? So aces or hearts. Well, these are the aces here. Okay, and then these are the hearts right here. Okay, and then so we can just count, right? So there's 13 on this row, right? So if we go all the way down here, that's 13 cards. Then we have 14, 15, 16 cards. Okay, so 16 over 52, and we've got it. Okay, so it's basically pretty much as easy as that. Now, let's go ahead and use the formula just to practice with that formula a little bit here. And so the thing that makes this difficult is that these are not really difficult, but it complicates things, is that ace and heart are overlapping events, right? You can get an ace and a heart, right? It's right here. Okay, so so this card here is overlapping. So they're not disjoint. Okay, so imagine your Venn diagram and those two sets would be overlapping. So if we went ace plus probability of heart, we would overcount, right? So right, there are 4 aces out of 52, and there are 13 hearts out of 52. So that would be 17 over 52. Okay, but we know the right answer is only 16. So what happened? We have one extra one in the overlap, right? So the general addition rule says we have to subtract off ace and heart. Okay, so we have to subtract off that one card that is in the overlap, which is 1 over 52. Okay, so when we subtract off that 1 over 52, we get back to our 16 over 52, which we know to be the right answer. Okay, make sense? So you got about 31% chance of getting an ace or a heart when you draw a card. Great. So maybe, yeah, let's go ahead and move on. Like I was saying, there's just so many problems on this page. It's more than we need to do. In fact, we've already done everything we need to in this section. Maybe we'll do one more to get kind of a slightly different problem going here. So why don't we do that last one on page 146 together? It says we have a 6-sided die and we're going to roll it. What's the probability that the number rolled is an even number or a number less than or equal to 3? Okay, so probability of even or less than or equal to 3, something like that. Okay, and it's a great example of how counting can be more effective than the formula sometimes. So what I would do is I would simply list out all of the possibilities for my roll of the die. Okay, and so which ones are even? Well, let's see, 2, 4, 6 are even. Which ones are less than or equal to 3? Well, these. Okay, so we just simply count the number that are in that set. So you can kind of imagine a Venn diagram in your mind. We could draw it out if you want, but basically it's these three plus these two over here. We don't want to double count the two, right? So we just say 1, 2, 3, 4, 5. So there's 5 ways out of 6 of getting either an even number or a number that's less than or equal to 3. Okay, so 5, 6 would be the correct answer there. All right, so that's the addition rule. Let's talk about the other kind of compound event we have. Okay, so sometimes it's an or, it's A or B, right? So imagine you're applying for a job and it says, okay, you either have to have 5 years of experience or a certificate, right? And then so that's an or. So one or the other will suffice. But sometimes you apply for a job and they say you have to have both of them, right? So you have to have 5 years of experience and a certificate, right? So it's similar, but it is different, right? So the and is more exclusive, right? So you have to have both of them simultaneously or kind of in a row, right? So sometimes in life you need both of two or more things, right? So what happens with the and? Okay, so if the or is addition, um, I guess it's not too counterintuitive. The and would be some kind of multiplication. Okay, so if the events are independent, then the probability of A and B is probability of A times probability of B. Okay, so with the or, we had the addition rule, right? And if the events were disjoint, the formula was easier. If the events were overlapping, then the formula was more complicated, right? Same thing holds for the multiplication rule. But instead of disjoint, we think about independence. Okay, and you might say, well, don't those sound similar, right? To be disjoint and to be independent, don't those sound kind of similar? They do sound similar, but they're actually exact opposites. Okay, if two things are disjoint, then they can't happen at the same time. So if one happens, then the other can't happen. So they're actually the exact opposite of independent. Okay, so we should probably define what independent means. Okay, so we say that two processes are independent of each other if knowing the outcome of one process provides no useful information about the outcome of the other. Okay, so I think it's probably best if we jump into some scenarios here. Okay. So let's say last night you're playing Monopoly, right? And you're really hot at Monopoly. You keep winning. You get lucky, and so you think, well, maybe tomorrow I'll drive over to Wyoming and play the lottery, right? And because if you get lucky in Monopoly, maybe you'll be lucky in the lottery. Well, that's just not how things work, right? You can win a lot at Monopoly, and it just doesn't have any effect on winning the lottery. They are independent processes. Does that make sense? So you guys try the rest of these. So these pairs of scenarios, these pairs of events, and tell me if you think they're independent or dependent. So on your paper there, just write I or D next to each one of these, and depending on whether events are independent or dependent, the multiplication rule is more or less complicated. Okay, so give that a try. Just kind of use your intuition there. Okay, what do you think? You gain weight, you eat fast food for dinner every night. Were those two things dependent or independent? Did they, yeah. Yeah, if you gained weight and you were eating fast food for dinner every night, it was probably some kind of relationship there, right? So in other words, it's kind of like an association, yeah? So independent events are not associated, dependent events are associated. Okay, speeding on the interstate, being pulled over by a police officer. What do you guys think? Dependent or independent there? Yeah, I think dependent. Now, it doesn't mean every time you speed, you get pulled over, right? I mean, I'm speeding all the time on the interstate, but not by much, but a little bit. And so I don't get pulled over every day. It's just, every few years I might get pulled over. So just because you sped once, it doesn't mean you're going to get pulled over. But the more you speed, it is more likely, right? So there's an association there. Okay, owning a dog, growing an herb garden. What do you guys think about that one? Yeah, probably independent. Robbing a bank, going to jail. Yeah, probably dependent. Okay, so again, people can get away with robbing a bank, but if you keep doing that, you're more than, pretty likely going to go to jail at some point. They just tend to go together. Okay, so that's what it means to be independent or dependent. And so depending on if it's dependent or independent, the formula will be more or less complicated. So let's do some calculations with this rule. And so this is pure probability, but the reason we're talking about probability is so we can understand samples better. So let's think about samples. Okay, so let's do some small samples. We'll start small to make the math easy. And then once you understand the basics of the math, you can ramp it up to much larger samples very quickly and easily. So we'll start with a small sample of 2, and then we'll look at another slightly larger sample of 5. And you can imagine here that maybe we're doing some taste testing or some market research. Maybe you work at, like Heinz, right? Heinz ketchup, one of these condiment companies, and you're looking at the market for sauerkraut. Okay, so do you know what sauerkraut is? I think it's kind of like a fermented cabbage, and so it's pretty common to put it on like hot dogs. Um, or and so it turns out that it's not as popular as I imagined. It's only about 21% of people that like it. Okay, so the probability that somebody likes sauerkraut is actually fairly small. It's about 20%. Okay. And so let's take a sample of people. And again, to make the math easier, we'll start off with a very small sample, just 2 people. And so what is the probability that both people like sauerkraut? So what I'm going to do is I'm going to rewrite that statement in a form that will let us use the multiplication rule. So if both like it, what does that mean? It means the first person likes sauerkraut and the second person likes sauerkraut. I'm going to abbreviate because otherwise the writing gets really um, kind of heavy. So the probability the first person likes it and the second person likes it. Because if that's the case, then both people like it. Why did I do that? Well, because I have an and, right? And I know that ands can be broken up into a multiplication. It's called the multiplication rule. Okay, but we have to be careful here because we need to check for independence. Okay, and so what's our population? Well, we can kind of imagine here maybe this is everybody in the country, right? So if you randomly select 2 people from at large in the country, then they're going to be independent of each other. If the first person likes it, that does not change the probability that the second person likes it, right? Now, if you chose 2 people from the same family, that might be different, right? But we're going to choose from a large population, so we do have independence. So how does that help us? Well, I know each of these probabilities. They're each 21%, right? So I have 0.21 times 0.21, so that's 0.21 squared, which is about 4%. Okay, so you randomly select 2 people. What's the probability they both like sauerkraut? It's actually pretty small. In fact, it would be unusual to select 2 people who both like sauerkraut because it's under that 5% cutoff. Remember that 5% rule we used to define unusual? So I would say yes. It would be, or it is unusual because 0.0441 is less than 5%. Okay. And so there we go. We're working with this multiplication rule. Let's make the sample a little bit larger, right? Because samples of size 2 are so small. They do exist. People can get information from them, but Usually we're thinking of things like, like 50 people or 500 people, okay? So we don't want to jump up to 500 just yet. Let's keep it, workable here, but larger than 2. So let's do a sample of size 5. Okay, so we're going to randomly select 5 people. What's the probability that all of them do not like sauerkraut? Okay, so we're going to randomly select 5 people. What's the probability that all of them do not like sauerkraut? Okay, so how would that work? Well, if all of them do not like sauerkraut, I'm going to write this out in kind of it'll appear to be a strange way. I'm going to say the first does not like it. Okay, so the first does not like sauerkraut, so I'm going to abbreviate it. And the second is a not like. The third is a not like. The fourth is a not like. The fifth is a not like. Okay, so all of them do not like it. That's how that's how you get all of them not liking it. The first and the second and the third and the fourth and the fifth all do not like it. So why would I write that? Well, because of the ands here, right? So when you're talking about a sample of 5 people, that's getting kind of complicated, right? And so one of the nice things that these probability rules allow us to do, I think of them as basically allowing us to take apart this complicated event and break it into smaller pieces. Okay, and that's kind of a good strategy for working with problems in general, right? If you have a complicated thing you're working on in life, right, you'll often break it down into smaller pieces and work on those smaller pieces. And that's what we're going to do here. Okay, so I'm going to say, well, that's the probability that the first doesn't like it times the probability the second does not like it times the probability that the third doesn't like it. And I think you're getting the idea here. We just keep going here with the multiplication times the probability the fourth doesn't like it times the probability that the fifth doesn't like it. Okay, so how does that help us? Well, we know each of those probabilities, or at least we can, right? What's the probability that somebody does not like sauerkraut? Well, it's the complement of liking sauerkraut. So it's like rain and not rain, right? Either it's going to rain or it's not, and either you like sauerkraut or you don't. So if there's a 21% chance that somebody likes it, then there's a 1 minus 0.21 chance that they don't like it, right? Which is 0.79. Okay, so you have a 79% chance of any one person not liking sauerkraut. So 5 people randomly selected from a large population are going to be independent of each other, right? So if you're talking about 5 people from across the country, yeah, they're all independent of each other. Now, if they're 5 people from the same family, that might be different, right? So we have to be careful there. But so what do we have? We have 0.71 times 0.71 5 times. Okay, so once you get the hang of these problems, you definitely don't need to do as much writing as I'm doing here. I'm just trying to get everything to line up in the formula so it all makes sense. And then once you get better at these, you can save yourself some writing. Yeah. Okay, so that's 0.71 to the 5th power. And then calculator time. We pull out the calculator. So 0.71. We raise that to the 5th power. Oh, sorry. My mistake. That's not 7.1. It's 7.9. I calculated it right, and then I started writing the wrong numbers over here. My apologies. 0.79, 0.79, 0.79. So if you were confused, then it's my fault. Okay, 0.79 there to the 5th power. Go back and do that again. Okay, so we're going to go 0.79. We raise that to the 5th power. And so it's not super likely, but it's certainly not unusual. You got about a 31% chance that would happen. So 0.3077. Okay, so again, just imagine you're doing some kind of market analysis, taste testing, kind of analysis, right? And you want to see people's opinions about sauerkraut. So you get a random sample of 5 people. How likely is it that all of them say they do not like it? It's definitely not impossible, right? There's a 31% chance or so of that happening. So it's not unusual because 0.3077 is more than 0.05. Okay. So that multiplication rule really gets us back to thinking about stats nicely. So good. The last part on this problem is a special problem. Okay, it's got some special language there. We call this the at least one problem. So when you're doing your homework, if you hear those three words, if you read those three words, at least one, you know it's a special kind of problem. And so what you'll want to do is run back to this problem here on page 148 and just try to make, just kind of line it up well with this problem here. Okay, so again, it's the at least one, and it's setting us up for a very special scenario here. Okay, so what does it mean? What am I getting at here? Well, okay, how would it happen that at least one of the 5 like sauerkraut? Okay, so we're going to take a random sample of 5 people. I want to know how likely it is that at least one of them likes sauerkraut, right? Sometimes that's a relevant question, right? Sometimes for something to work, you just need one, one thing to work, right? Or sometimes for something to fail, you just need one of them to fail, right? So this at least one actually does pop up sometimes in life. So, okay, if we have a sample of 5, what's the smallest number of people that can like sauerkraut? Well, you could have, the worst case scenario would be 0, right? So the smallest number of people that could like sauerkraut has got to be 0, right? At the other end, you could have a lot of people, right? You could have everybody liking it. Wouldn't be very likely. We already saw that just getting 2 people out of 2 liking it is kind of small, but it is theoretically possible that all 5 like it, right? Okay, and then any number in between is also possible. You could have 1 person liking it, you could have 2, you could have 3, you could have 4 people liking it. Okay, so which ones of these represent at least 1? Well, any of these represent at least 1, right? If 1 likes it, then that's at least 1. If 2 like it, that's at least 1, all the way on up to 5, right? There is one possibility, though, that's not in the at least 1. It's the none. Okay, and this happens every time you have one of these at least 1 problems. There's none, and then there's everything else. Okay, so there's basically 2 groups, and they're non-overlapping. They're complementary events. Okay, it's like rain and not rain. Okay, so since they're complementary, we can use the complement rule, right? So what's the complement rule? Well, again, if it's like rain and not rain. So the probability of the complement is 1 minus the probability of the event. Okay, so what I'm saying is that the probability of at least 1, I'm going to abbreviate it here, AL1, at least 1, since it's the complement of none, then it should be 1 minus the probability of none. So why would we do that? Well, we already have this number, right? That's what we calculated up here. How likely is it that none of them like sauerkraut? Okay, so we already have the number, and so we just throw it down into here, and we've got it. Okay, so we go 1 minus 0.3077, so that's about 0.6923. So there's about a 69% chance in a sample of 5 people, at least one of them will like sauerkraut. Okay, so it's pretty likely, right, that at least one of them is going to like it. It's probably not going to be all 5, right, but at least one of them. If that's the question, then we have a pretty high chance of that happening. Okay, so that's really interesting, right? We're making probability statements about various samples, so it sets us up nicely for sampling theory. Okay, so I'd like you guys to try another one of these, and just like with the addition rule, we have tons of extra problems in the notes here. Let's see, so that, no, let's see, so that answer will go down if it said at least 2. Yes. Good. So good question. Yeah. So if it said at least 2, then we would definitely get a smaller number there. Good. 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 That's good intuition there. Because it's harder to get at least 2 people liking it. Good. Okay, so like I was saying with the addition rule, it was just like with the addition rule. These sections of the notes are just packed and kind of overflowing with problems. I'm not going to do all of these. Um, we basically already talked about all of the rules here. So I'd like you guys to try one of these. Okay, so I think I've mentioned that some of the rules of probability, early probability, were developed by gamblers or discovered by gamblers. So we have a lot of stuff about cards and dice and coins. Another kind of problem you see a lot of is something like this, where you've got like a box or a bag of objects that are either numbered or colored. Okay, and the reason we like these is because it's really easy to create test questions. So you might see something like this on exam 4 or on the final. Okay, so we've got a box. There's 6 blue marbles in there, 5 red and 2 green marbles. Okay, so we're going to select 2 marbles from the box with replacement. Okay, what is the probability that both are blue? The first is blue and the second is green. The first is green and the second is blue. Okay, so what do these words mean? With replacement, it has a double asterisk next to it, so we should probably consider what that means. So the with replacement means a selected individual is placed back into the population and can be chosen a second time. Okay, so the scenario is, okay, we've got this box, and in the box are all of these different, all these marbles with different colors, right? And so you're going to reach into the box without looking. You're going to choose a marble. You're going to note the color of the marble. Okay, so you get a blue one, right? And then you put the marble back in. You shake the box again, so it's all nice and mixed up. You reach back in. You pull another marble out. Okay, so that second marble, does it remember the color on the first marble? No, right? So in other words, the fact that you got blue for the first marble will not affect the probability of getting blue on the second marble. I hope that makes sense, and I hope that that seems correct, right? So what am I saying? With replacement is independence. Okay, so if you see those words with replacement, it's a nearly perfect synonym to independence. And we like independent events. Independent events are easier to work with. The probability rule is. Now, sometimes in life, we don't do things with replacement. So if we don't have replacement, then we're saying that they're dependent events. Okay? So if you take the first marble out and it's blue and you put it aside and then you reach back in, well, getting blue on the first one really does change the probability of getting blue on the second one, okay? Because they're dependent. You didn't put the first one in, right? So with replacement, independence; without replacement, dependence typically. So you guys try all 3 of these problems, okay? You're gonna reach in twice. What's the probability that both are blue? What's the probability the first is blue, the second is green? What's the probability the first is green and the second is blue? Okay, use that multiplication rule for independent events to help you analyze this. Okay, and this really is how the world works, or at least a part of the world. When it comes to likelihoods, this really is how it works. So I'll go quiet for a couple minutes and let you guys do this one. Okay, so probability that both are blue. How do you get both being blue? Well, the first one is blue and the second one is blue. Okay, so and you can break it up with multiplication. So probability the first is blue times the probability the second is blue. And then, so that breaks that complicated event into two simple events. So we just need to find the probability of each of the simple events, right? So 6, right, out of how many are there? Well, there's 13 marbles here, right? So we have 6 out of 13 for first being blue. And then if you put the first one back in, you reach back in, then it's the same probability, right? So we've got about a 21% chance of that happening. Okay, and we could verify this empirically. We just bring in a box with the right number of marbles, and we could all just kind of just simulate this, right? And we would see that that is the correct probability. Okay. Okay. Did anybody get part B? What's the probability that the first is blue and the second is green? Did anybody get that far? Did I give you enough time? Great. That is exactly correct, Armand. There's about a 7% chance of that happening. So not impossible, but probably not very likely. So why did I write it like that? Well, because I can break it up now with the multiplication rule. Okay, and it's the basic multiplication rule because these events are independent, because we're putting the first one back. Okay, so the probability the first one is blue, well, there's 16 out of 13 blue, and then green, there's not as many of those, there's 2 out of 13. So that's going to be 0.0710. It wouldn't be unusual, but it's not very likely either that you would get the first one being blue and the second one green. What happens if you reverse the order? What's the probability the first is green and the second is blue? So let's write that out. Sometimes you just kind of have to trust the formula. Probability is a very subtle branch. Of all the branches of math, I sometimes think it's the most subtle. And so sometimes you just have to trust the formulas on how it works. Your intuition can really fail you when it comes to probability, I've found over the years. So probability, the first one is green. Well, there's 2 out of 13 that are green, and then there are 6 out of 13 that are blue. So notice it's really the same thing, it's just in a different order. So we have the same probability. Okay, so that's not going to change. Maybe we'll do one more, just a quick one here at the bottom of 148, and then we'll move on. You start rolling a die, and you get patterns, right? And you start wondering, well, how likely is this pattern, right? And so let's say you get 4 ones in a row. How likely is that? Okay, I mean, it doesn't seem like it'd be very likely, but would it be shocking to get 4 ones in a row? How likely is that? Well, if they're all ones, right, you're going to do it 4 times. So the first is a 1, and the second is a 1, and the third is a 1, and the fourth is a 1. So that's multiplication, right? So it's probably the first one is a 1 times the probability the second one is a 1 times the probability the third one is a 1 times the probability that the fourth one is a 1. Well, when you roll a die, there's a 1/6 chance of getting a 1, right? So what is that? That's 1/6 times 1/6 times 1/6 times 1/6. Okay, so that's going to be 1/6 to the 4th power. Turns out that it's extraordinarily difficult to get 4 ones in a row. That's not 0.08. That's not 8%. That's 0.0008, right? So that's like that's like a little bit less than 1 in 1,000, right? Okay, chance of happening. So, okay, let's see. Laura's asking about this one here. So she's not getting the 0.0710. So let me show you how to do that. So when you multiply fractions, you multiply across, right? So that's going to be 2 times 6, so that's 12. And then we're going to divide that by 13 times 13. So notice I'm putting parentheses there. And so that gives us the 0.071. The other way of doing this is one fraction at a time. So I can go 2 divided by 13. You got it? Okay, good. Times 6 divided by 13. Okay, so good. All right, any other questions there? So that's our addition rule, both the basic and the general addition rule. And now we've covered the multiplication rule in this simple case where you have independent events. Okay, so let's see, where are we at? We've done complement rule, we've done the general addition rule, and we've done the multiplication rule for independent events. Okay, so what's left? Well, we need to cover the general multiplication rule when we don't replace the marble, right? When we have dependent events, right? What happens to the multiplication rule in that case? Well, to understand that, we have to understand this thing called conditional probability. Okay? And so what's conditional probability? Well, it's actually very much like a conditional distribution in a contingency table. Okay, so we're going to condition on some event happening. Okay, oh, sorry. We're skipping this page. It's just more examples there. So we're going to come down here to page 150 and talk about conditional probabilities. Okay, so what is a conditional probability? Well, we're going to condition on some event already happening. Okay, so a conditional probability is the probability that an event occurs given another event has already occurred. And there's a formula for it. It goes like this. The probability of A given that B has occurred. Okay, so let me just tell you how to write this, how to say this. This would be said probability of A given B, or given that B occurred. So what on earth is this all about? Well, I think you already know kind of the basic idea here about conditional probability. And let me just demonstrate it. Let's go back to the idea of weather for a second. I need somebody to play along with me here, okay? And there's not really any wrong answer here, I think. Can somebody tell me, or if you want, you can even look it up online, that's fine. Can anybody tell me what the probability of rain is today in, say, Salt Lake or maybe Davis County? And could you just put it in the chat? You can make up a number, you can look it up on weather.com, whatever you want. But I need somebody to play along here. What is the probability of rain today in Salt Lake County? 1%. Yeah, if you look outside, I'm not seeing a lot of clouds here. So sure, 1% is possible. So you're saying, in other words, that you don't think it's going to happen. Okay, great. That's perfectly fine. Now, so one of the things we use probabilities for is to make predictions, right? We find these useful, right? If you want to do a picnic, this weekend, it's helpful to know what the weather forecast is, right? So we go to the weather forecast, and then they make a prediction about whether or not it's going to rain, okay? And then you can use that to decide if you want to have your picnic. So what we're going to do with conditional probabilities is we're going to make the same prediction, but we're going to have new information. Okay, so here's the new information. Let's say I'm asking you the probability of rain, and that very second I ask you about rain, we all hear a very large clap of thunder, right? So it's like really loud, like startling thunder bolt or thunder sound there. What happens now to the probability of rain now that you've heard that thunder? Can anybody play along with me on that? Okay, so Is it still 1% chance, or is it less likely? Is it more likely? Okay, great. Thank you, Julia and Laura. Yeah, so it increases, and then Julia's got a number there for us. 40%. Perfect. Yeah, great. So yeah, what happened? It went from 1% up to 40%. It went way up. Why is that? Because these two events are, they're not independent of each other, right? Sometimes we hear thunder and we don't get rain. Sometimes we get rain without any thunder, but those two things are definitely connected with each other, right? So, if you hear thunder, especially like really loud thunder, it does probably mean the likelihood of rain is higher. Yeah, that's exactly what this means. Okay, so we're trying to make a prediction about an event, and we simply are able to update our prediction because we have some relevant information. That's the idea of conditional probability. Okay, and it's not actually that bad to work with. I think you'll find it's pretty straightforward. So there's a formula for it. It says the probability of A and B divided by the probability of B. So we can calculate it. Okay, so we just need some other probabilities to do that. And if we take this formula and rearrange it, if we just multiply both sides of this formula by probability of B, we get another way of writing out the multiplication rule, which is to say it's the probability of A given B times the probability of B. Okay, so this is the general multiplication rule. And it's presented here on your formula card right here. So we're knocking these out, right? We've got almost all of them except for the expected value, which we'll do on Tuesday. Okay, so it's the general multiplication for dependent events, and let's practice with it. So our favorite way of thinking about probability is to use contingency tables. So that's what we have here. Okay, and so the Pew Research Institute, or the center, they are one of the top polling companies in the country. So they're right up there with like Gallup and Harris Poll and all of those other important polling companies. And so they do all sorts of social, political data. And the idea is, we want to understand what people are thinking and their opinions about various things. And so this table, in this poll, they were asking about people's opinions about various political groups, right? So, there's the Democrat president, there are Democrats in Congress, right? And then there's Republicans in Congress, right? There's lots of other political groups, obviously, but to make this something we can do in class, we'll just focus on these three, okay? And then so they've got a large sample, right? So they called up these more than 4,000 people, and when they actually do these polls, they have a long list of questions, right? It's hard to get people to participate, so when you get somebody to participate, you try to get as much out of them as you can, right? So there's a ton of questions they ask, and they ask, how do you feel about this or that? And in this case, the answer, they were asking, do you approve or disapprove about this person or this group, right? And so we've got the results for three of these: the president, the Democrats in Congress, and then the Republicans in Congress. So what are these numbers? Well, for example, there were 842 that disapproved of Republicans in Congress. Yeah. So in other words, 842 times when people were asked about Republicans in Congress, they were saying they disapprove, right? And then 736 times that people were asked about Democrats in Congress, they said they approved, okay? And so let's use this table to practice with our conditional probabilities. What's the probability that a randomly selected U.S. adult approves given that they're being asked about Democrats in Congress? Okay, so I'm actually going to add in another part to this problem so we can get kind of a better feel for what it means to be dependent. So I'm going to add in a problem. What is the probability that somebody is approving. Okay, and I'm just going to leave it just any question. Okay, so if you get a randomly selected person and a randomly selected person in question, right? Are they approving of the person you're asking about? Well, how many people are approving? There's 2,119 out of the 4,223. Okay, so if we pull out the calculator there, 2119 divided by 4,223, we're looking at about 0.502. Okay, so that's a different question that I wanted to add on here for reference. Now let's actually answer question A. Okay, so now instead of approving and trying to, so if you have a randomly selected person in one of these questions you're asking them, there's about a 50% chance they're approving, right, of the person you're asking them about. But I'm going to give you a little more information. I'm going to tell you that they're about to be asked about the Democrats in Congress. Okay, so does it change the likelihood of approving? Okay, so now I want to know what's the probability the person is approving given that they're being asked about the Democrats in Congress. Okay, so there's two ways of doing this. We can use the formula, and that's great. It's a little bit slower, but it's important to do that. It's important to see how the formulas work. Then we'll do it a second way that's actually faster. Okay, so let's do it the slow way by using the formula. Okay, and so what does the formula say? Well, the formula, it's this formula above. Okay, so it's this formula here that we're going to look at. So A is approving, and what's B? B is Democrats in Congress. Okay, so wherever I see an A, I'm going to have approving. Wherever I see a B, I'm going to have Democrats in Congress. So let's fill that in. Okay, so what's the probability of the person approving and being asked about Democrats in Congress? That's the numerator, right? So that's this part. Then we're going to divide by the probability of the second event. So the second event is Democrats in Congress. So probability of being asked about Democrats in Congress. Okay. So how many people were both approving and being asked about Democrats in Congress? Well, that's these folks right here. Right? So there's 736 of those out of the 4,223. That's our numerator. Then in the denominator, we're saying what's the probability that somebody was being asked about Democrats in Congress? Okay, well, how many of those are there? Well, there are 1,382, right? And so the probability of being somebody being asked about Democrats in Congress is 1,382 out of 4,223. Okay, so it is more complicated. It's not impossible though. You just have to line up all of the events correctly into the formula. And then notice that those denominators actually cancel out, giving us 736 over 1382. So if we run over to the calculator there, that's 736 divided by 1382. So 0.533. So what does that mean? Well, let's compare it back over here to the probability of somebody just approving in general of, so it's kind of like averaged across all of the categories here. Well, when you're just asking in general about approval, it's about 50%. But if you know they're being asked about Democrats in Congress, notice that the approval actually goes up a little bit. It's a little bit more likely that they approve. And what that tells us is that at that point in time, the Democrats were more popular than maybe some of these other groups, right? Maybe they're more popular than the president, or maybe they're more popular than Republicans, or maybe they're more popular than both, right? Because when you have that little additional information there, the approval does go up a little bit, okay? And that also shows us that there's an association there between approval and which group you're talking about, right? So at this point in time, they were not, it wasn't like they were all equally likely to have, an equal approval, right? And that kind of happens, right? These things fluctuate a little bit. Sometimes one group is more popular than the other, and then things kind of change, and so it kind of fluctuates. All right, so that's a demonstration of how we can use our conditional probability formula. Okay, let me show you how to do it more quickly without a formula. Okay, and so I think I've mentioned this a few times about how we love the formulas for probability. We need them to, especially for more complex stuff, we need them for the more complex analysis. We also need the formulas to really prove to ourselves we know what we're doing. But sometimes in this class, in the 1040 class, I find that it's just kind of easier if you count instead of using formulas. What do I mean? Well, let's redo this one here. Okay, the probability of approving, given that they're being asked about Democrats in Congress. Well, if they're being asked about Democrats in Congress, then we're right there, yeah? And so we can ignore everybody else, okay? And that makes it easier, right? There's only 1382 in here. How many of those 1382 were approving? Well, 736 out of 1382. Notice it's the same number that we got over here. Okay, and I did that without even using a formula at all, right? And so do it that way if you can, right? It's just faster, and it's one of those cases, it's kind of an unusual case where doing the fast and easy way actually typically leads to better results. Okay, it's harder to mess that up, right? Whereas with the formula, it's very easy to mess that up. Okay, all right. Let me do another one. What is the probability that a randomly selected U.S. adult is being asked about Democrats in Congress given that they approve? Isn't that the same thing? Okay, so you have a particular question that was answered by a particular person, right? And so we're trying to guess if that question was about Democrats in Congress. And I'm going to give you a little information. I'm going to tell you that the answer to that question was approve. Okay, so, and we've already seen above that those two things are dependent. So knowing that the person answered approves for that question should change the probability they're being asked about Democrats in Congress. Okay, it sounds like this one here, but it is different. Okay, up here we're trying to predict the likelihood. We're trying to predict if they approve, given that we knew they were being asked about Democrats in Congress. But here it's exactly the opposite. We're trying to predict if they were asked about Democrats in Congress, given that they were approving. Okay, so how can we do that? Well, let's use our counting technique. Instead of the formulas, let's just use the counting technique. If I know that somebody approves, then I know that they're somewhere in this part of the table. Right? If they're approving, then they have to be in the approving row. And if they're in that row, how many of them are being asked about Democrats in Congress? 736. So we just go 736 out of the total number for that row, 2119. Okay, no formula, we just get the answer. It's super nice and quick there. 35%. So it's different, right? It's definitely a different probability because the order when it comes to conditional probabilities is quite important. Okay, it can change things dramatically sometimes. So then we can answer another question. Are being asked about Democrats in Congress and approving independent events? We kind of already answered that up here, right? We saw that approving, and if you have information, additional information about what, if you're being asked about Democrats or not, it does change that probability of approving, right? So we would say, well, the probability of approving is not equal to the probability of approving given that you're being asked about Democrats in Congress, right? We proved that up here, right? We said it goes up if you're being asked about Democrats, which means at that point in time, the Democrats in Congress were more popular than the Republicans in Congress, or perhaps the Democratic president, right? So, so we would say, since having this additional information about the second process makes the probability of approving change, we would say the two events are dependent. Remember the definition of independence. It means if you know information about one process, it doesn't change the information about the other process. But here, knowing this information did change the probability of approving. So the events are dependent. Okay, they are not independent, therefore they're dependent. Okay, I want you guys to try one. In the next data set, it's kind of an interesting data set. We're looking at sleep and sector of an industry. Okay, so it's kind of like labor, and we're thinking about health and quality of life and maybe safety issues here. So I'll just give you another few seconds to write down anything you want here, and then we'll move on over to the next example. So it was done by the National Sleep Foundation, and everybody in this study worked in one particular field. They're all transportation workers. So some are pilots, some are truck drivers, some are train operators, and then some are bus, taxi, limo drivers. Okay, and so why do we care? Well, I mean, these are all people that are driving, big, heavy vehicles, and we don't want them to fall asleep, or that, well, they're piloting these big, heavy vehicles, right? We don't want them falling asleep and wrecking, right? And probably they also have some people on board with them, and we don't want those people getting hurt. So sleep is pretty relevant, right? Okay, so and so we've got sector of the transportation industry. So that's a categorical variable up on top for the row column variable. And then for the row variable, we've kind of grouped or binned sleep into three different categories, right? We have the people who are probably not getting enough, less than 6. We're getting people who are getting adequate sleep, and then there's a third group here of people who are getting the recommended amount, right? Okay, so 3 levels for the sleep variable. So that's another categorical variable. So you know that anytime you have a categorical versus categorical, we have a contingency table, right? So these contingency tables are everywhere. They're super useful for this kind of data set, this kind of data structure. Right? And so is there some kind of relationship between subsector of the transportation industry and amount of sleep they get? In other words, maybe, let me just kind of put it in concrete, way. Do truck drivers get more sleep than pilots, or vice versa, right? Or do bus drivers get less sleep than train operators, right? Maybe some sectors have, maybe their people are working, are overworked, right? Or maybe underworked, right? And so we want to see if, there's some kind of relationship there between the amount of sleep they're getting and what category they're in, what sector of the transportation industry they're in. Okay, so so it's a contingency table, and so for example, the 58 here, these are all bus, taxi, limo drivers who are getting plenty of sleep, right? The 19 here, these are pilots who are not sleeping enough, right? Which could be a huge problem for safety, right? So you guys give this a try. We've got several problems here, and we don't have a lot of time. We got about 8 minutes, so you could probably get a couple of these done, and then we'll finish up this next time. But definitely give this a try. I want you to pull out that multiplication rule and the conditional probabilities and give this a try. Okay, so I'll go quiet for maybe 3 or 4 minutes and let you guys work on some of these, and then we'll come back together and we'll finish out today with a couple of these. Okay, so I'll go quiet until about 12:46. How about that? Okay, so keep working. Any questions out there? All right, I'll just go quiet for a second. Okay, so let's see here. What's the probability that a transportation worker gets less than 6 hours of sleep per night, given that it's a truck driver? Okay, so the probability of less than 6, given that the person is a truck driver. Okay, did anybody get this? I recommend not using the formula. Okay, we've already used the formula once. Maybe when you're doing the homework, you use it a couple times. But for these contingency tables, much easier to just count. Okay, so if we know the person's a truck driver, then we can ignore all of the other categories. We know they're in here, right? And so there's 203 of those. Out of that group, how many were getting less than 6 hours? Just 35, right? So 35 over 203. So about a 17% chance that a truck driver is not getting enough sleep. Good. Thank you, guys. That looks correct. Um, let's reverse that. What's the probability that a transportation worker is a truck driver given that they got less than 6 hours of sleep per night? Okay, so let me come back to this for 1 second. I like to think of this as like kind of a like a like detective work. Okay, you're trying to figure out if a randomly selected person is getting less than 6 hours of sleep per night. I'm giving you this information that they're a truck driver, right? And so that additional information may change that likelihood. Okay, so now it's the exact opposite. Now I'm trying to predict if a randomly selected transportation worker is a truck driver given, and I'm giving you some information that they got less than 6 hours of sleep. Okay, so what happens there? Well, usually it can make a difference. Usually it makes a difference. Sometimes it's a big difference. Sometimes it's a little difference. Uh, Also, as far as getting the numbers right, usually this second piece of information tells you what part of the table to look in, right? So we look in this table or row for the denominator. So same thing here. For the less than 6, if they're getting less than 6, we know they're in here. So our denominator is the total for that group, which happens to be a row this time, right? So we have 104 people getting less than 6 hours. How many of them are truck drivers? 35. So we have a 35 over 104, which is about 0.337. Okay, all right. Use the contingency table to compute the probability that a randomly selected transportation worker is a pilot who gets 6 to 8 hours of sleep. Okay, so we call this a joint probability because two things are happening. It's a pilot who's getting 6 to 8 hours of sleep. So you can use the formula here. It's easier if you don't, though, and just go to counting. So who are these people that are pilots and are getting this adequate amount of sleep? Well, it's that group right there, right? Those are the only people in this sample who are both pilots and who are getting 6 to 8 hours of sleep. So we can just go right there. It's 132 over 795. And I believe that works out to be about 0.166. Good. Thank you, Laura. Perfect. Okay. What's the probability that two randomly selected transportation workers are both train operators if the selection is done without replacement? I know we're almost out of time. Let me just knock this one out. So if they're both transportation workers, that means the first is a train operator and the second one is a train operator. Okay. So we know that that's a multiplication. So it's the probability the first is a train operator times the probability the second is a train operator. But notice we didn't put that first person back in after we selected them, right? So we have to change that a little bit. It's now going to be probably the second one is a train operator given that the first one was a train operator. Okay, so it becomes a conditional probability there because of dependence. We have to stop there. So we'll pick back up with this one next time. But we're doing great with the time here. Everything's looking fine. Let's see, we're supposed to be getting to about 5.6 today. Yeah, so Tuesday we'll come in and we'll come back and we'll finish off chapter 5. We might have to use a little of next Thursday to do that, but either way, we'll have some time to review for test 4, and then just like I always do, I have a recorded review along with some practice problems that will be available in Canvas as an announcement soon. So anyway, we're in good shape here for our 4th midterm here that's coming up in a while. Do you have any questions for me as we break for the week? Nothing? All right. Well, if you do have anything that comes up, just shoot me an email and I will see you all on Tuesday. Take care, everyone. Thank you, guys. All right. Thank you. You too.